Hey there, future programmers. Let's talk data structures. Imagine you have a giant box of Legos. You can build anything, right? But without organizing those Legos, it's chaos. That's where data structures come in. In the world of computers, data structures are like those handy storage containers for your Legos. They are ways to organize and store data in a computer so we can access and use it efficiently. Just like you wouldn't store your Lego minifigures with your spaceship parts, we need different data structures for different types of data and tasks. Why should you care? Well, using the right data structure can make your programs run faster and smoother. It's like finding the right Lego piece quickly, instead of digging through a jumbled mess. So, whether you're building a website, analyzing data, or creating the next hit video game, understanding data structures is key. Get ready to become a data organization master. Let's start with the basics. Linear data structures. These are like lining up your Legos in a straight line, one after another. First up, we have arrays. Think of an array like a row of mailboxes, each with an address. You can store data in each mailbox, and you can access any mailbox directly using its address. Arrays are great for storing lists of items, like your top 10 favorite songs. Next we have linked lists. Imagine your Legos connected by little chains. Each Lego piece is a node, and the chain is a pointer that tells you where the next piece is. Linked lists are more flexible than arrays because you can easily add or remove items from anywhere in the chain. Linear data structures are the workhorses of programming. They're simple to understand and use, and they form the foundation for more complex data structures. So master these, and you'll be well on your way to data structure domination. Now let's talk about stacks and queues. Two more types of linear data structures that are super useful in everyday programming. These structures help us manage data efficiently and are fundamental concepts in computer science. Imagine a stack of pancakes. Each pancake represents a piece of data. You can only add a pancake to the top, that's called pushing, and take a pancake from the top, that's called popping. This is a simple yet powerful way to manage data. This is how a stack data structure works. It's a LIFO structure, meaning last in, first out. The last item you add is the first one to be removed. Queues, on the other hand, are like a line at a ticket booth. They follow a different principle. The first person in line is the first person to get a ticket. FIFO, first in, first out. This ensures that the order of processing is maintained. You and queue add items to the back of the queue and dequeue, remove them from the front. This method is crucial for tasks that need to be processed in the order they arrive. Stacks and queues are everywhere in computer science. They are the backbone of many algorithms and systems. Stacks are used for things like undoing actions in a text editor or managing function calls in a program. When you hit undo, the last action you performed is the first to be reversed. Queues are used for handling tasks in the order they arrive, like printing documents or processing network requests. This ensures that each task is completed in a fair and orderly manner. See? Data structures are already all around you. From the way you organize your tasks to the way your computer processes information, stacks and queues play a vital role in making everything run smoothly. Understanding these concepts can greatly improve your problem-solving skills and efficiency in programming. They are not just theoretical ideas, but practical tools that you can apply in real-life scenarios. So next time you write a piece of code or tackle a complex problem, remember the power of stacks and queues. They might just be the key to unlocking a more efficient solution. Linear data structures are great, but sometimes we need something more flexible. Linear structures like arrays and linked lists are straightforward and easy to understand. They allow us to store data in a sequence, making it simple to traverse and access elements. However, their simplicity can also be a limitation when dealing with more complex data relationships. That's where nonlinear data structures come in. These structures are designed to handle more intricate connections and relationships between data points. They allow for more dynamic and versatile ways to organize and manage information. Instead of a straight line, these structures branch out like a tree or connect like a web. This branching and connecting nature makes them ideal for representing hierarchical and networked data. First, let's talk about trees. Trees are a fundamental type of nonlinear data structure that mimic a natural hierarchical system. Imagine a family tree with grandparents at the top, parents in the middle, and children at the bottom. Each level of the tree represents a different generation, and the connections between them show the relationships. This hierarchical structure is exactly what a tree data structure represents in computer science. Trees are used to model relationships and hierarchies in a way that is both intuitive and efficient. Trees are used for organizing data in a way that makes it easy to search and retrieve specific information. For example, Binary search trees allow for quick lookup, insertion, and deletion of elements, making them highly efficient for various applications. Next, we have graphs. Think of a map with cities as nodes and roads connecting them as edges. This is a perfect analogy for understanding graphs. Graphs are all about relationships. They are used to represent connections between different entities, whether they are cities, people, or even web pages. They're used to represent networks like social networks, transportation systems, or even the internet itself. Graphs can model complex interactions and dependencies, making them invaluable for a wide range of applications. Nonlinear data structures might seem a bit more complex, but they are incredibly powerful tools for solving a wide range of problems. They provide the flexibility and efficiency needed to handle complex data relationships and large datasets. Understanding them will open up a whole new world of programming possibilities. By mastering nonlinear data structures, you'll be equipped to tackle more advanced and sophisticated programming challenges, making you a more versatile and effective developer. Section 5, Data Structures in Action, from websites to social networks. Okay, we've covered a lot of ground, but how are data structures actually used in the real world? Let's take a look at some cool examples. Ever wondered how websites load so quickly? They use tree structures to organize the content on the page, making it lightning fast to find and display the information you're looking for. No more waiting around for ages for a web page to load. Social media platforms like Facebook and Instagram, they rely heavily on graphs to represent the connections between users. Every time you like a post, comment on a photo, or send a friend request, you're interacting with a massive graph database. These are just a few examples of how data structures are used every day to power the technology we rely on. From online shopping to streaming services, data structures are the unsung heroes working behind the scenes. Section 6. Choosing the right data structure, a matter of efficiency. With so many different data structures to choose from, how do you know which one is right for your program? This is a common dilemma faced by many developers, both beginners and seasoned professionals alike. The choice of data structure can significantly impact the performance and efficiency of your code. It all comes down to efficiency. Efficiency in terms of time and space complexity, which are crucial factors in determining how well your program performs under different conditions. Think of it like this. If you need to store a small fixed number of items and access them quickly, an array is a great choice. Arrays provide constant time complexity for accessing elements, making them ideal for scenarios where quick access is essential. But if you're working with a large, constantly changing dataset, a linked list might be a better option. Linked lists allow for efficient insertions and deletions, which can be particularly useful when the size of the dataset is unpredictable or frequently changing. Each data structure has its own strengths and weaknesses. For instance, arrays are great for random access, but can be inefficient for operations that involve frequent insertions and deletions. Arrays are great for random access but slow for insertions and deletions. This is because arrays require shifting elements to maintain order, which can be time-consuming. Linked lists are the opposite. They're fast for insertions and deletions but slow for random access. This is due to the need to traverse the list from the head to the desired node, which can be inefficient for large lists. The key is to understand the trade-offs and choose the data structure that best suits the specific problem you're trying to solve. By carefully considering the characteristics of each data structure, you can make an informed decision that optimizes your program's performance. It's like picking the right tool for the job. The right data structure will make your code more efficient and easier to work with. Just as a carpenter wouldn't use a hammer to cut wood, a programmer must select the appropriate data structure to achieve the best results. Section 7. Key takeaways. Your data structure toolkit. Congratulations, you've just completed a crash course in data structures. Let's recap the key takeaways. 1. Data structures are essential for organizing and storing data efficiently in computer programs. 2. There are many different types of data structures, each with its own strengths and weaknesses. 3. Choosing the right data structure for the job can make your code faster, more efficient, and easier to maintain. 4. Data structures are used everywhere in computer science, from basic algorithms to complex applications like websites and social networks. You now have a solid foundation in data structures, a valuable tool in your programming toolkit. Section 8. Next steps. Level up your programming game. Ready to take your newfound data structure knowledge to the next level? Here are some next steps. Practice, practice, practice. The best way to learn data structures is to use them. Start by implementing simple data structures like arrays and linked lists in your favorite programming language. Explore advanced topics. Once you're comfortable with the basics, dive deeper into more advanced data structures like trees, graphs, and hash tables. Solve real-world problems. Challenge yourself to use data structures to solve real-world programming problems. You can find plenty of practice problems online or even try your hand at building your own projects. Remember, learning data structures is a journey, not a destination. Keep practicing, stay curious, and never stop exploring the fascinating world of computer science.